Why does measuring a quantum qubit change its state? Have you ever wondered why measuring a quantum qubit alters its state? This question dives deep into the fascinating world of quantum mechanics and how it shapes our understanding of information. Let's break it down. A quantum qubit is a fundamental unit of quantum information. And like a classical bit that can be either 0 or 1, a qubit can exist in a superposition of both states at the same time. This means it can be in a combination of 0 and 1, described by a mathematical function known as a wave function. When we measure a qubit, something interesting happens. The act of measurement forces the qubit superposition to collapse into one of its possible states. This is not just a passive observation, it actively changes the qubit state. Before measurement, the qubit has a probability for each state, allowing it to exist in multiple states simultaneously. Once we measure it, the wave function collapses to a definite state, either 0 or 1. This phenomenon is rooted in the principles of quantum mechanics. The measurement process interacts with the qubit, causing it to randomly select one of the states based on the probabilities encoded in the wave function. In practical quantum computing systems, such as those using superconducting qubits, measurement often involves coupling the qubit to a resonator or cavity. The measurement signal interacts with the resonator, which changes its properties depending on the qubit state. However, this interaction can lead to unwanted effects. For instance, the measurement photons can be absorbed by the qubit or excite other modes, causing transitions to states outside the intended computational basis. Moreover, the measurement process is limited by the no-cloning theorem and the uncertainty principle. These principles prevent us from making perfect measurements without disturbing the quantum state. Efforts to measure a qubit without changing it, known as quantum non-demolition measurements, face challenges due to physical effects like photon-induced transitions. In essence, measuring a quantum qubit changes its state because the quantum superposition collapses to a definite state. The measurement interaction physically disturbs the qubit, possibly leading to transitions. Fundamental quantum rules ensure that we cannot measure without some disturbance. Practical implementations often involve coupling to measurement devices that can induce additional state changes. Understanding these measurement-induced changes is vital for reliable quantum computation and error correction. Advanced techniques aim to reduce the impact of measurement on qubit states, improving fidelity in quantum information processing.